Let me do 4, that's true. And 4 is the quotient of two absolute continuous functions where the bottom is never 0. So in particular, bottom is never 0 on A to B, so there's this delta where basically just pick the minimum of this function on A to B. Continuous on A to B. Yeah, so ultimately you kind of want to look at I mean, you want to set up the whole epsilon delta thing for absolute continuity, but you want to look at this. And so let's get a common denominator, G of B, G of A. B. So 1 over delta squared. Yes, I did multiply the first one by G of A over G of top and bottom by G of A, second one top and bottom by G of B. Um, uh, less than or equal to, because this is bigger. And you can add and subtract f of A, G of A. So from here, you can factor out A, G of A. And I'll be trying on the following in a second, but this is this thing you've done a million times, 511. And here, factor out an f of A. A. Um, and let's say. Minus F of A. F of A here, G of A up there. And F and G are both continuous on closed AB, so they're bounded. So let's say this is less than or equal to M, regardless of what A and B are, or A is. Really, now I just use the definition of absolute continuity for both of these. Um, that's really that. Set up the like what we well, yeah, to set up the use the definition of absolute continuity here. I mean, I just kind of remember what all of that is. At least the definition I use. So both of these are absolutely continuous. I'm gonna do it for both A or both F and G. So we just want it to be squared to M epsilon. Same for G. Yeah, F and G are both absolute continuous. Do that. And when I write this, it's implied that this could be a finite sequence of intervals. Yeah, so means Well, let's just go over here. Use this. Well, it's epsilon over delta squared over epsilon delta squared over 2m, so this is. Yeah, so the key thing that makes this pretty easy, it's just G never vanishes, continuous on AB, so it's bounded from below. All right, so any of the 5 through 8, do you want me to go over? Or are those pretty? I mean, it's really the, let's say, 2 and 3, that's, when I look at it, it's really tricky. I'll go back and kind of see how to fix what I had. So yeah, I mean, do you want me to go over any of the 5 through 8? Those are more straightforward. Are you still there, John?
Yep.
Yeah.
Yeah.
Yeah, do you want me to go over any of the 5 through 8s?
I was gonna say if we could do number 5 probably.
Yeah, sure. Let me get a drink of water. Yeah. Yeah, 5 is just that little variant of Chevychev's inequality, really. You want to remember. Yeah, so So let's say lambda, no, I forget which. Nothing special about 0. So yeah, you want to show the measure of this for any delta convergence to, that's what convergence and measure is. Yeah, so for large enough n, on most of 0 to 1, this is small. Can make the measure of this set here as small as we want, no matter how small. Yeah. Yeah, so. So if you forget that little variance, I would just kind of work backwards. So instead of integrating from 0 to 1, it's integrating over delta. But this is bigger or equal to delta on the set here. So it's delta squared. X is here. So integrate basically 1 here, you just get the measure of E delta. That's what you're going to do. And here. Right, so it says. And we're assuming this is 0 because that fact converted to F now. Let's see. Yeah, 6 is that example we've done a few times already. Kind of like those small, like that kind of set that kind of like you can like form a sequence of intervals 0 to 1, 1/2, 0 to 1/2, 1/2 to 1, 0 to 1/3, 1/3 to 2/3, 2/3 to 3/3, 0 to 1/4, et cetera, to form the characteristic function of that. That's going to be convergent in measure to 0, but not pointwise convergent to anywhere. 7 is just rationals is countable, so. I mean, do you want me to go over any of the 6 and 7 briefly, or?
Uh, maybe 7.
Yeah, okay, so just explicitly. Um. Basically explicitly show that the rational has measures. So explicitly construct an open set U. Such that the rationals are in U and the big measure of U is less than epsilon. So just say, let's say the rationals, is just enumerated as Rn. So you make this nice and small, that it sums up to something less than epsilon. Let's say, let's say, so this is certainly open, just countable union or union of open sets. Let's say this is U, problem says U. So. The measure of U, countable subadditivity. Less than or equal to epsilon over. Yeah, and I guess really I want two, so this is plus 1. I mean, if it just adds up to epsilon, that's fine. But strictly speaking, it says less than epsilon. You want me to go over 8 or?
Sure, why not?
Yeah, so this is the converse. Guess this 4, 5, and 7. Those make sense.
Yeah, that makes sense.
Okay. All right, so 8. I'm trying to remember. I think someone did this in recent class in a little easier way than I like to do it. As the converse to Lucen's theorem. You have a function on 0 to 1. Where for any epsilon bigger than 0, there's a closed subset F. Where the measure 0, 1, take away F is less than epsilon, and F is continuous on F. Show that F is measurable. So if F is measurable, then basically F is continuous on every, or there exists an F closed where F is little f is continuous on big F, and the measure 0 to 1 take away F is less than epsilon. So it's like it's a converse of Lucen's theorem. The function has basically the conclusion of Lucen's theorem. Or if the conclusion of Lucen's theorem is true, then F is measurable. Yeah, okay. Okay, so, okay, FM. Opposed. Uh, Yes. Okay, so. F is a set of measure zero, so the intersection of all of these. Or it's easier to. Okay, so this is. Complements turn into intersections. And this is less than or equal to each one of these for every n. Okay. So yeah, that means this equal. Right, so. Now I want to show that F is measurable. I'll say this is open. You don't really need that F is bounded. So you can write this as. Say, F. The goal is to prove this is measurable. This has measure zero. Prove that. There. So this is measurable. So because F is this union here, this is gonna be union. So let me do, so this. Measurable again, because I've measured zero, because it's intersection of something with measure zero, and hence that zero. This here. Well, this is exactly same thing. Like definition of F restricted to Fn. Inverse image. That's a set of all X in Fn where F of X is the theta. And F is continuous on Fn. Each one of these inverse images is open. Just from continuity. Fn is continuous on Fn.
Sorry, could you repeat that again? I'm sorry.
Yeah. F is continuous on Fn. So each one of these is open. So in particular, this is countable union of, well, but so in particular, this is open and it's good. Or at least, I mean, relatively open in that. The point is, it's better. So this is. So it's the union of two measurables.
Okay.
If it's continuous on the set, then the inverse image is an open set in Fn. Really an open set intersect Fn. It's still either way countable union of measurable sets.
Okay.
I mean, alternatively, you can do Burrell-Contelli, do this 1/2n, that sums up. The sum of the measures finite, so then. This is actually, yeah, I think this is one of the homeworks I assigned. For the Burrell-Contelli argument to do this.
Mm.
One of the homeworks. I'll look for that. But this is an easier way to do it.
Okay.
Does this kind of make sense, or?
Yeah.
Um. Anything you want me to go over?
No, I think I'm
Like,
also.
except for like 2 and 3, did kind of everything I do makes sense?
Yeah. Yeah, I did.
Anything?
Do we have to know convergence in the norm?
Yeah, that's just that's what I had a second ago. It's simply. So in general, on some set E, convergence in LP is just, this is 0. And convergence in L infinity, you're just using the L infinity norm. It's the infimum of all essential upper bounds.
Right.
Go to the minimum. Because the L infinity norm is essential.
Okay. Yeah. Okay.
You would
I
have
believe
to
I'm.
which homework this is.
Hmm.
No, there was this one homework where you said you had listed someone else's solution.
Yeah, which was this.
This one, it was not the final, it was probably not more paid,
That'd been like,
I think
5
it's
or
like
6.
5 or
Okay.
6.
Okay, yeah, I'll think about 2 and 3. I mean,
I would start by looking at 1 5, because I
Yeah.
remember you mentioned that after.
right, yeah. I mean, 2 and 3 are they're a little exotic. I wouldn't really worry too much about them. Probably I'll add them on the list, actually. But I'll still kind of curious about them. There's only 4 and 8 are good problems. All right, yeah, and I might do this just on Zoom in future. The only animal that came here, so.
I think.
I want to say hi or
I don't miss. Okay.
everything.
I was saying, I think Andrew's in like the one business.
Yeah, Andrew's is away. He mentioned that, so he would definitely. Well, I mean, that's a possibility for Zoom.
Okay. Well, thank you very much, Josh. I appreciate it. I need
Yeah,
to.
sure thing, sure thing. Yeah, sorry about the 2 problems I wasted your time on. That was.
Oh, that's okay. That's okay.
You picked a prelim that had the one prelim that had 2 of the weirder problems that. I think almost every other prelim, like, yeah, I've done this before, I've done that before. These 2 are like, wait a minute.
Yeah.
All right. See you next time then.
Yep. I'll see you on Tuesday.
Yeah, take care. Apologies.